So I guess that during the last lecture probably I stressed you out a little bit with some of these theory. So this will be much simpler and much more hands-on, and you can sort of lean back and listen to some of these things. And I have sort of two examples that I want to show you that are practical examples, very much also related to experiments. And the main part will be to convey ideas, behind what's going on here. So for the first part, I have also some theory slides that are about chiral and cascaded master equations. And you can simply decide me that you want to see them or not. So you can either trade the theory part for the second part over here, which is more a hands-on experimental part. So we have to choose at one point, and I will ask you at the right moment if you want a more easygoing talk, colloquium style, or if you want something which is then deep theory again, where you really show you that we derive interesting new equations that are useful. But maybe you're at the level now where it's late in the afternoon where you want to go easygoing. Okay, so I will ask you at the right moment. So I would like to discuss now two topics that may have interest to you in the sense of being open quantum systems. And you can see two keywords. The word is open and the word here is many-body. And the first example will be chiral quantum optics. That's something as a quantum optician I've been very interested in, and I will tell you what these things are. And in the meantime, that's also related to experiment, but not yet at the point where one is doing the many-body part, even from the theory perspective. That's very interesting, and I will tell you qualitatively what the ideas are. The second part is entanglement by dissipation. We did some theory actually quite some time ago, and then finally an experiment happened that gave rise to a Nature paper together with a blood group on using dissipation to prepare certain entangled states. This was stabilizer pumping, and I can give you sort of the basic idea of what's behind it without going very complicated, but it's kind of related to what we were talking about in the last lecture. We do here Krauss operator engineering, You say, well, a certain Krauss operator, if you had them in the lab, this would do something really interesting, That the question is how do you engineer it, okay? And even get it in the lab. So Krauss operators are not used, well, to describe coupling to the environment, but you use it as an engineering tool. And the question is, how do we build them in the lab? Okay, so in this sense, let me start out with the first part, which is chiral quantum optics. And on the later slide, I have a review article cited that we wrote together with Peter Lodahl in this group, who is a solid-state physicist in Copenhagen, Arno Rauschenbeutel, who is an experimentalist in Vienna, soon moving to the Humboldt University in Berlin, on the atomic physics side, and we also participated in this review from the theory side, so I will cite it afterwards and you can read that. This has all of the references that are relevant here. It's a little bit short on theory, but it has a lot of the vision of why these things are important. Okay, on the theory side, so I have to tell you what chiral quantum optics is, and I will give you very qualitatively a snapshot of what the ideas are, what's special about this system. This is a way, as you can sort of lean back. And then there's this theory behind it, which is a theory of cascaded quantum systems. I can tell you what they are. And if you want, I can give you a derivation of the cascaded or chiral master equation, which is also a Lindblad master equation, but sort of more complicated, which is actually very interesting. And then the basis has several interesting properties. And I will give you a hand-waving argument. But if you want to see the details, then the last part we have to drop. Okay? So what is chiral quantum optics? Let me give sort of a snapshot at the very beginning, what these things are that we are talking about. We are talking here about, for example, networks. Okay, so what is a quantum network? A quantum network is, for example, that you have nodes, okay, in space. This can be short distance, or maybe very long distances. You can think of these nodes as being little quantum computers. And you would like to connect these quantum computers, think of this as being a little one over here, this as being one, that's another one over here. You would like them to exchange quantum information, quantum communication, and you would like to build now certain channels. Think of them, for example, as being waveguides that you put, and then these quantum computers would like to communicate with each other, being able to, for example, send quantum information from here to here. This would be a way of, for example, scaling up quantum computers. You build little modules, of a few qubits. and then you would like to connect them together and scale them up, then you would need something like that. But I will talk about the photonic channels over here, where these stationary qubits, this could be some atoms in our case, or maybe ions, are converted to photons and are then sort of reabsorbed over here by some protocol, like in quantum state transfer. But I would like to talk about very, very special photonic channels over here that I find very interesting in terms of properties that give rise to interesting, completely new class of many-body system, which is something that we call chiral coupling. And let me explain to you what they are. And sort of mention right away, this is to do with unidirectional coupling. So these are photonic channels where propagation can only go one way. And I make the side remark here that these things are naturally realized in nanophotonic devices. And an atomic physics experiment is the one by Arno Rauschenbeutel that I will explain now on one of the next slides now in a little bit more detail, where the basic idea is the following one. I'll explain it then afterwards really in more depth. But you take a nanofiber and you trap atoms up here, just a small distance above the nanofiber. And if you ask the question, these atoms over here can emit optical photons by spontaneous emission into the waveguide. And it turns out that due to the nano size over here, you will find that the emission is essentially unidirectional. So you break the left-right symmetry. You can even make it so extreme that almost all of the photons go in one way. So you got a system here that's actually very interesting, because you got your nanofiber over here, and in the ideal way, you would have your atoms that are sort of floating up here, And these atoms, when they emit a photon, they can send this photon into the waveguide. It only goes one way. It can be absorbed by the next atom or not, This can emit, but when this second atom emits, it also goes one way. So you have a unidirectional coupling. You're breaking left-right symmetry. And this is what we mean by chirality. And this is an example of a chiral light-matter interface. I will explain afterwards very briefly and qualitatively what the physical origin is. It is actually classical electrodynamics, what's underlying is, but we're using these things at the end in a quantum way. So this gives rise to interesting many-body physics here, where you have unidirectional coupling of systems. And this atom can talk to this one, but this one cannot talk back to this one over here. And then does it give rise to interesting new many-body physics. You will see that intrinsically, this is an open system dynamics. And I will argue then the details for this thing a little bit later when I make this quantitative. Now what's sort of nice is that all of these things appear naturally in nanophotonic devices. So if you are a solid-state physicist or an atomic physicist, you talk about coupling, you usually get these things free, or you can really try to make it almost perfect and sort of engineer this thing. The bad part with these setups is that, what's the percentage of photons that goes into the fiber relative to the one which is emitted in free space? This would be decoherence, whereas this is, so to say, the good photons, and you want to be in the limit that all of the photons are going into the fiber. And this is, of course, the main experimental challenge in all of that. So the combination of this thing is an example of a setup, but I said it's much broader. And this thing over here makes this thing an interesting story. And I would like to give you now sort of a little bit a review from a very qualitative point of view, what this chiral quantum optics is about and nanophotonics. But I would like to start out what it is not. Okay, so many of you, when they hear the word chiral, and they say, this is somebody talking about nanophotonics and the topology and all of that. And this is what I try to illustrate over here. There's many groups out there that do these fantastic experiments where you make photonic nanostructures that exhibit topology, and then you got these edge modes. Maybe I should start this thing again here. Okay, where if you have a photon, it will sort of propagate around here. You can see that this is a chiral edge mode. Light can only propagate there. It's like in a quantum Hall effect, and so that's very interesting, super interesting. It's not what I will talk about in the following, okay? I talk about chiral light-matter interface, where it's more symmetry broken in the way that I will explain it. So it's not what I will do, just to make the difference clear. What I will talk about is something which is mentioned, explained in this review out there, which is much more the chiral coupling between light and quantum emitters, sort of protected by symmetry and not topology. Yeah? And I want to explain to you now what the underlying physics is and take the experiment by Arno Rauschenbeutel as the example. But you will see afterwards that the whole thing is much more general, and we can engineer it also in completely different systems. So there was this paper a few years ago by Arno and his group members. They did these things for gold particles, but then also for atoms. Of course, the atoms is the part that we are really interested in. The science paper was for gold particles. This was purely classical over here, but then there was later on a paper in Nature Communication where they replaced the gold particle by single atoms. What's the reason that if I have a two-level system, if you have spontaneous emission that goes into the fiber, that the photon goes one way but not the other? The reason behind it is actually spin-orbit coupling. It's a purely classical electrodynamics effect, And what is the spin-orbit coupling here? Well, let me sort of explain it like this, that imagine that you have here a fiber over here. So to zero order, if you got a plane wave which is propagating, we'll simply say, well, what electrodynamics teaches me is this, that if I have a plane wave, I have a certain k vector that goes in a certain direction, and of course, my light polarization has to be orthogonal to that. So you have a transverse electromagnetic field. But remember that here we talk about modes that are propagating in a nanofiber, something which is maybe 200 nanometers or a few hundred nanometers of this order of magnitude. And so the consequence of all of this is that you have to satisfy, of course, also Gauss' law, like the divergence of the electric field is equal to zero. So what does that mean? That in the forward direction you got a plane wave, but in the sideward direction you have very strong confinement. We talk about the confining mode, propagating in your fiber. So you have a Gaussian over here, some confinement, and you have a propagating forward direction over here, like in the case of a plane wave. If you would like to satisfy the Gauss law as an equation, what it means is that your light propagating with a k vector like this, and this is your component of the light polarization, gets a component of the light polarization which bends forward, okay? But it bends forwards in the way, transverse, you have a confinement like a Gaussian, forwards you're propagating. The forward component of your polarization vector is actually out of phase, with the transverse vector over here. So if I give you a polarization vector and I say that this one plus I, imaginary part, this one over here, then all of you will tell me this is sigma plus polarized light. Right? But it's very strange, sigma plus polarized light, because it means that this is sigma plus polarized sort of in a direction like here in this basis, whereas the propagation goes this way. So imagine now that I put an atom up here, okay, above the fiber, and I drive this atom perpendicular to the fiber with a laser, which is sigma plus polarized light, so that the photon emission from this thing is in this direction sigma plus polarized. So this photon, when it goes into the fiber, can then only propagate one way. This is called spin-orbit coupling. It's a purely classical effect. We just combine it here by quantum mechanics, by taking as the underlying atom-light interaction, this spin-orbit phenomenon. Yeah, this is kind of universal, and it's one example, but I will show you afterwards that you can actually easily engineer this also in some other systems. So by chiral, I simply mean that we have here atoms coupled to a waveguide, and when the emission happens, then it goes essentially one way. And then we would like to make many body systems out of these things. This is the goal of the story, and this is one example. The main problem, with these experiments at the moment in atomic physics is this, that this background emission rate is actually quite non-negligible, and you have to then construct like what Jeff Kimball does here. This group, you would like to pull these atoms into nanostructures to get very strong couplings and all of that, which is highly non-trivial. But also very interesting. And but I will now give a discussion. Suppose that all of these experimental problems are solved. Let's now try to look at the many-body physics that comes out here. And this is sort of the experimental setup underlying these things here. And so let me give you now sort of in a colloquium style just the intuition of what's happening here on the physics side in these chiral many-body systems. Okay? So what we want is let's imagine that we have this atom that I just said, is floating above this fiber. And this atom can undergo a transition to the ground state over here and emitting a photon into the fiber. You can this is exactly the theory that we did in the last lecture. We have an atom emitting into a one-dimensional continuum of modes. It's exactly the model that we had before, so you can apply it over here. But it's sort of special in the sense that when this thing goes down, normally you have a photon component left and right, and this will be normally equal, in most of the situation. But we are now interested in the one where in the photon emission you couple differently between left and right. There's an emission rate gamma that goes to the left and a certain one to the right, and they are different. And chiral means this broken symmetry left and right. I emphasize this is not due to topology, but this is due to the fact that we sort of broke the symmetry, for example, via the spin-orbit interaction, or maybe we can engineer it also in another way. And the ideal case would be the one where you get nothing to the left and everything goes to the right. This is sort of the ideal chiral system that we would like to discuss. You will tell me immediately that actually this is rather useful. For example, if you're an experimentalist and want to build a quantum network and you have your little qubit over here, you can sort of route it left or right, depending on the chirality. So this corresponds, has an immediate application as routing of qubits if you want. This is one of the examples. But I guess the examples we have now in the following sort of get more interesting. So we generate here right-moving photons. It goes over here, and we know with certainty that the photon then goes to the right. And in these experiments by Arno Rauschenbeutel, a pretty small percentage was actually emitted into the waveguide, but the probability left and right, as I remember, was something like 95%. So it's amazing how this spin-orbit coupling gives rise to, very good asymmetry. The first point that I would like to emphasize over here, that chirality, this left-right emission over here, implies very much that these waveguides here are infinite, that we have open boundaries. In other words, that we talk about an open quantum system. So chirality in the form that we discuss here only appears in the context or in connection with having an open quantum system. I can sort of easily give you an argument. Suppose that this is not an open quantum system, this would amount to having a mirror over here, then this photon would be reflected, and of course you would get something on the left out. So if you emit right away to the left or then reflected here to the left, there may be a certain time delay that may be interesting and give rise to some physics. But at that point, so the openness of the system, that this photon goes out and never comes back, is sort of very fundamental for the discussion that I will have now in the following. So chirality and open systems are two things that for me in my following discussion now always come somehow together.
The spin-orbit coupling is in the atomic, in your atoms, or is in the interface?
Okay, so the spin-orbit coupling sort of comes in like this, that I said before that if you got your nanofiber, okay, if you got the photon, which this kind of a polarization, sigma plus, sigma minus, which goes this way, is emitted into the fiber, then it goes in one direction. And how do the experimentalists break by hand this symmetry? It is broken by hand, okay? It's simply that in the basis that corresponds to, a basis where you have sigma plus, sigma minus in this sense, when you write down the atomic basis, you have all of your Zeeman levels and you create a two-level system. But now in the coordinate system where you did optical bumping with sigma plus light that comes here from the side to bump everything over, that you got a two-level system which emits a sigma plus photon here, then this photon which is emitted then goes unidirectional to the fiber. So it's really your experimental preparation that breaks the symmetry, and there's no fundamental topology reason or whatever, something very deep behind it. It's just broken symmetry by hand, if you want to. Okay.
Citation laser comes perpendicular.
Yeah, that's right. Yeah, right. Okay. Now you can see that it gets kind of interesting when you have here a many-body system, because the interesting part about chiral atoms is this thing that if this suppose emits only one direction, then it means that this atom will be able to talk to this one over here. So this one goes down, this photon propagates over here, and with a certain probability can kick up the atom over here. But when this atom over here at the end decides to emit the photon itself, it will go unidirectional here. So this means that atoms only talk to atoms downstream. This atom never finds out that there's other atoms over here, whereas of course this atom learns about this one, but doesn't know about the atoms here to the right. So we have a broken left-right symmetry, and this gives rise to a new class of many-body systems that we normally don't have in nature in this form. And you might ask, does it lead to something useful and also something maybe interesting from the physics point of view? So atoms only talk to atoms on the right-hand side over here. Okay, let me sort of bring this thing a little bit to the point and try to discuss the relevant master equations. And I will quote here results, and then we can sort of decide if I really give you also the formal derivation behind it. And if you feel a little bit tired, I'm very happy to skip it and rather do then some more experimental stuff afterwards. Let me just make you sensitive for what these things mean. So normally, when in quantum optics, we talk about dipole-dipole interaction. What is dipole-dipole interaction? You got an atom over here, and you got an atom over here. Both of them are two-level systems, okay? Exactly as I sort of indicated over here. So suppose now that what happens is this, that this first atom, this is simply flip-flop interaction, sort of goes down here. It can emit a photon, maybe as a virtual photon. You can integrate it out, and this thing will be lifted up. And of course, we have completed a symmetric process going the other way. So if I tell you that, in dipole-dipole interaction, we write down flip-flop Hamiltonians of this type, of course, in free space, they would go down like 1 over r cubed. I mean, this is just a flip-flop that two atoms will do. It would be completely symmetric. And all of you would agree that this is the kind of Hamiltonian that you would get if you integrate out the radiation field, maybe as a sort of a reservoir. So when you derive your master equation for a many-body system, these are the kind of things which you get. So you get Hamiltonians that are very obvious. These are just a flip-flop that two of these atoms do with the 1 over r cubed in free space, and we will write it now down in a minute of what happens if you replace it by a waveguide. A waveguide, of course, focuses all of the photons, in this unidirectional one-dimensional system, and then it's not 1 over r cubed, but actually infinite range. But the situation that we have in chiral optics, chiral quantum optics, is actually the second one over here, okay? So you can see that you would have a term where this thing goes down here, emits a photon, but this photon only goes one way. It can be absorbed by this one, but then this one emits, it sort of goes here to the right. So this is this broken left-right symmetry that I was talking about. So at that point, I mean, I can ask you, what's the Hamiltonian for this thing, to describe this kind of an effect. And maybe some of you might say, well, the first term up here was just one going down, the other one up, and the second one was just the opposite. So why don't we just leave out one of these terms over here, and you might write down a Hamiltonian of this type. But is everybody happy with this Hamiltonian? So all of you remember that in quantum mechanics, in the first lectures you were taught that observables, Hamiltonians have to be Hermitian, except they can be non-Hermitian if you do continuous measurement theory, but then it's something much more sophisticated and deeper, as we saw. But this Hamiltonian obviously cannot be the answer, okay? And of course, to some extent, I've given you a hint before what the answer to the story is. This problem of these chiral interactions, something like this, only makes sense if you talk about an open quantum system. So what we should derive is really a master equation and not write down a Schrödinger equation with a strange interaction like this, which is non-Hermitian, in order to describe it. And this master equation is actually called the Cascaded master equation. Was derived in quantum optics about 20 years ago in papers by Crispin Gardner and also Howard Carmichael and so on. And I can give you afterwards a derivation behind it. I would just like to show you this equation. And the answer at the end is you can make this thing self-consistent with this argument by writing not the Schrödinger equation, where this thing is a Hamiltonian, but the master equation that has a certain structure where terms like this appear exactly describing this kind of effect, but they must come packaged as a master equation to be self-consistent. Okay, so you need a master equation treatment to make sense out of all of these things that we have over here. Okay, so you can see that even from the theory point of view, that's kind of interesting. So let me now be a little bit more specific. So suppose that you put on your hat as a theoretical quantum optician, and you would have now two atoms over here. We don't have a driving laser here for the moment. We can easily add this thing afterwards. So atom would be up here, then emit the photon left, right, with this maybe broken symmetry. And then you do your standard homework, as we did it in the last lecture, that you derive, for example, a master equation. I mean, how would this work? I mean, the argument will sort of go that you say, well, I got a system coupled to an environment, which is given by my fiber over here, which I want to be infinite. I want a continuum of mode. I do not want this thing to be a cavity. If I have a cavity, I would be doing quantum electrodynamics of two atoms inside of a cavity, maybe a multimode cavity. No, I don't want that. I want this thing to be open. So if a photon is emitted, this thing should go out to infinity and never come back, never returns. That's very important for what we do. It's not a cavity. So at that point, you will declare these fiber modes here, this continuum of fiber modes, exactly as we did in the last lecture, to be your heat bath or your environment, and you would integrate it out, assuming this Markov approximation as a quantum reservoir. And at the end of the day, what would you get? Of course, the master equation would be just of the structure, with the Lindblad term that we derived now in the last lecture. It must have this form, and you would just happily write down this thing. So the question is, what's this equation over here for the case of symmetric emission and for the case that we have an asymmetric chiral emission, okay? And we will get two different results in this context, okay? And what I would like to do in the next few slides is this. I would like to show you the answer and then intuitively discuss this thing. And the cascaded one will be the one that maybe you will not understand in all detail immediately. And if you want, I can then give you a hardcore derivation. But I think all of you are pretty tired today, so maybe we skip this part and I remain hand-waving. And maybe at the end show you a few other slides that are maybe more easy to digest as a replacement for that. Okay, but let's decide when you see that. Maybe you get so fanatic that you really want to see it, okay. Okay, so there's now two cases. One is the standard case, okay? In the standard case, you would have an atom here and here, and this is the one that I indicated by the dipole interaction. This atom would emit a photon. It's completely symmetric left and right, okay? And we integrate everything out. And of course, we are coupling this thing to a 1D waveguide. This makes it actually very interesting because in a 1D waveguide, it's not like what you have in space, where you have dipole-dipole interaction, and it's 1 over r cubed, the coupling. The electric field goes out, and with the distance, the coupling gets smaller and smaller. Due to the fact that this is a 1D system, you can see that the master equation is the following form. Here's your system Hamiltonian, which is just the atom over here. You can assume that this is driven by Rabi oscillation and very happily emitting photons into the waveguides over here that we have integrated out, so they can play ping pong here along. And this ping pong here along, can you see this term over here? Sigma plus, sigma minus, sigma plus, sigma minus. This was exactly the flip-flop term that I was arguing before, for this mutual absorption. This comes out over here. It's a little bit special to the 1D geometry that you get an infinite range interaction, and that we got, this is position of one and the other one. This is a speciality of the 1D character of our waveguide, that this looks like this. So if you ask, what is that? Well, this is exactly the Hamiltonian you do expect from 1D dipolar emissions. What would you expect for these, quantum jump operators over here? Well, it turns out, suppose that you sit out here with a photodetector on the left-hand side, and I ask you now, the photodetector makes a click. So which atom has emitted the photon? You don't really know. I mean, it can be the first one, the second one, the third one, and so on. So it should not come as a surprise that the master equation that we have over here would actually not only have single atom terms, sigma I, ith atom, and then sigma I over here, but it has cross terms. So this simply comes from the fact that in this 1D situation, you get collective spontaneous emission, okay? This is master equations, a sticky master equation that has been discussed in many papers, and here's one of the references for these things, okay? So this is a standard world as you do quantum optics with this completely symmetric situation. And now we can go to the next part and ask, what changes now if you go to a cascaded quantum system? We have a cascaded quantum system, then we have this unidirectional coupling over here. And then it turns out, well, after some work, and I said that I can derive it, but you look very tired, so maybe I won't do that, you get out that, well, of course, it is a Lindblad master equation. We are very happy about this thing. But it has now two terms that's quite interesting. So let me start out with this effective Hamiltonian term over here. This effective Hamiltonian term, if I give you a single atom, a bare atom over here, it has Hamiltonian H1. What did we find for the effective Hamiltonian in the last lecture when we said Wigner-Weisskopf? We simply added an imaginary part to the upper state frequency to describe the spontaneous emission, and this was, in the sense of continuous measurement, this Wigner-Weisskopf Hamiltonian that at the end appeared in a master equation. And indeed, you can see here's a term H1, and here's this imaginary term gamma over 2 sigma 1 plus minus. This is the decay of the excited state of my first atom over here. This looks like makes a lot of sense, okay? And of course, you have a similar term over here for the second atom, okay? But see the extra term that comes in here? Sigma 2 plus minus, this is exactly this asymmetric term that I was talking about, that sort of, one can go down and kick up the other one. This is a non-Hermitian term, but in the effective Hamiltonian, this is allowed if the whole structure, the master equation that comes out, is actually of Lindblad form. This is non-Hermitian, this Hamiltonian from the very beginning. And this is the extra term that overappears. And this is the term, this, you know, if one goes down, it kicks up the other one. But if this goes down, it does not kick up this one, okay? This is the term how it appears. So in the master equation, this makes a lot of sense. It would not make any sense if you just write down a Schrödinger equation with this thing. Then it would be a non-Hermitian Hamiltonian, and your quantum mechanics teacher would be quite unhappy that you are happy with that. What's now the last term over here? Sigma, you know what this is over here? See, sigma is a collective jump operator. So what's the meaning of this operator? Actually, this has a very simple meaning. I said before, suppose that you sit out here with a photodetector and you see a click of the photodetector. So this means that one of the atoms, but you don't know which one, emitted a photon. And so the jump operator simply expresses this thing by being a collective jump operator, sigma 1, either the first one went down or the second one went down. And this whole package of this whole thing over here turns out to be a Lindblad master equation. So it is a valid form of a master equation. This is what we get from this derivation. A small side remark I would like to make over here is this, that the position of the atoms over here, in principle, there would be atomic positions as phases appearing. They can always be reabsorbed in the definition of the sigmas. So while on the last slide over here, there was a lot of, you know, sine and cosines that we had over here, you know, that depended on the relative distance. You know, it's like if you have two atoms a certain distance, it's like an interferometer. And that's the reason why the sines and cosines appear. But over here, this from here to over here, it just picks up a phase, and it turns out that we can gauge away the phase. So there's no position dependence here because we were able to gauge away all of these extra phases that appear in this context. Now, this equation has one interesting property, and it takes a little bit of a while to work it out. So if I write down this cascaded master equation, it is for this composite, you know, this atom plus this atom here together. For this Hilbert space of, you know, tensor Hilbert space 2-level atoms, tensor product 2-level atom over here. What should this master equation reduce to if I trace out from this master equation, if I trace out from this master equation over here, this second atom. So I have an atom, 2-atom master equation, and I'm tracing out the second atom. What should the result be? I mean, the first atom never finds out that there's a second atom because the second atom cannot dock back. You know, it's like in a black hole. Okay, okay. And so it means that if I take the trace over the second atom, I get the reduced, I get the master equation out for the first atom alone, and it's a standard optical Bloch equation for the single atom, which has radiative damping, you know, standard equation. Okay, and it just never finds out that there's another atom downstream. If you want to do the same thing, you know, for the second atom, then of course the first one will appear as a source, you know, term, and it will not reduce to the single atom equation. So the second one always knows the presence of the first one, but not the other way around. Okay, this is what this chirality means and this brokenness. Of course, if you put a mirror over here, this photon would be reflected and the first atom would find out, and all of these things are not valid. So this is the reason why this openness of the system here is very important. And this answers the question, who was asking, one of you was asking the question about, you know, if I have input fields, for example, that are non-classical for the second atom. Who was asking this question? Was it you? Okay. So suppose I want to do the following problem. Go back to the last lecture. I made the assumption that I had a two-level system and we were calculating spontaneous emission, doing all of these nice calculations, but we assumed the vacuum state at the beginning, okay? So let me now assume that I don't want to take a vacuum state, and I give you something very complicated. I would like to drive my two-level system by anti-bunched light. How would you do that? Well, there's a source out there, anti-bunched light. It's called single atoms. If I give you a single atom like the first one over here, and I would drive it with my Rabi terms over here, I would excite it. It would emit a photon. This photon would propagate then here to the right, you know, in this picture. And this photon can be absorbed by the second one over here. So if you want to describe these dynamics of the second atom, you know, driven by non-classical light over here, you would write actually down this cascaded master equation to describe these things. So I would not describe the photons as input states that I write down in my stochastic Schrödinger equation, quantum stochastic Schrödinger equation, but I would rather do a theory of the source which in this case is a two-level system, and then have the emitted photons as part of this theory over here, sort of, can be absorbed by over here. So this cascaded master equation also answers in a very practical way what you said. You do a theory of the source over here, and well, this is sort of the answer in the most simple case. So this would give you the very interesting answer. I have a two-level system, and I drive it with anti-bunch light. Then you don't get Rabi oscillations, you get something much more complicated, but this equation here has the answer. And there's some papers out there by Scott Parkins and Crispin Gardner quite some time ago that studied, for example, these things based on equations of this type that we have over here. So you can see that our master equation knows the causality, and this physics that we talk about, broken left-right symmetry, is sort of embedded over there. Okay, and you can generalize things to n atoms and chiral networks, and we have done this in papers. The most recent one, I guess, is the one over here. So here's now this part that I guess that you sort of concluded that we should not really. So the majority wants that we should maybe skip this now, and you can look at it as an appendix and at home when you have a sleepless night. Is that what we should do? And we should sort of move on this more qualitative discussion what the physics is about. Should we do that? Okay. I think that the organizers say yes here because they also.
Can I just add? Sorry. Tomorrow I'll be discussing quantum feedback networks, and I think I can give a derivation.
You give a derivation. Okay, very good.
Example of a series product. So.
Okay. So in that sense, this will be taken care of tomorrow. Okay.
Also in your review paper, or that the derivation is in your review paper? No?
No, this review paper was published in Nature, and this was all of the nice things that we wrote there at the end were edited out because this has to be understood by everybody out there, and this was too restrictive. But we actually wrote nice papers about these things, also including time delays, solving the quantum stochastic Schrödinger equation with matrix product states. So there's rather complicated theoretical formulations out there. This was work done together with Hannes Bichler. And so there's rather sophisticated things about these things on the theory side that I don't really want to touch here, like time delay and in this sense quantum feedback. This would be part of these things, but I'm not touching on this because I was supposed to give an introduction to quantum optics, and otherwise, he would give me a minus point for that. Okay, so the slides that I will not discuss are now here, unidirectionality, and then giving you a physical example. Here you see my derivation of unidirectional couplings, how these things come about. You see the very nice, noise operators here with time delay, because if this photon is emitted, it appears with a time delay over here. We let this time delay go to 0 here at the very end, and then then comes really again my integration of my stochastic Schrödinger equation over here. The interesting part is that the time delay that you have leads to this asymmetry between the ping pong, so one can emit and the other one absorb, but not the other way around. So it's this delta function over here that appeared, that leads to all of this magic. You can look at that. That makes this thing so asymmetric. And then you see this, wow, this is this, we have flip-flop, but this is, so we have a ping pong and the pong ping, and this is only the ping pong term, I guess, sorry. That appears over here, coherent interaction asymmetric, and you get all of that, and then you can derive the master equation. It comes in different forms. End of appendix. Okay, so we make now a little quiz, okay, if you all understood that. Okay. Let's sort of continue again on this very qualitative level and state, why is this useful? And one very simple answer to this would be that if you do, for example, quantum state transfer, this comes in very handy, this unidirectionality, because there you would sort of have a photon wave packet which is emitted over here. And there's a quantum state transfer protocol that we had in an old paper written many years ago, and there were many papers afterwards, and also great experiments by Rempe, and also with superconducting qubits, for example, some recent work on quantum state transfer. The idea is this, that if you can shape the wave packet to be completely symmetric, normally a wave packet coming from spontaneous emission is like an exponential. It has a sharp beginning and then it has an exponential tail. If you can engineer a coupling over here, time dependent in such a way that the wave packet that comes out is symmetric, then we have argued in these protocols that the emission can be time reversed by the absorption over here, and you find a perfect quantum state transfer where a qubit can be sent from here to over here. And we had a paper last year in Physical Wave Letters where we could show that even that a system like this is immune to injected noise, and we put some error correction in addition to that, so it's long stories behind this thing. But you can see the advantage here of chiral couplings that are in principle perfect state transfer. I don't want to say much more because you can look at these protocols over here, and that's not the point of my talk here. Let me give you a second example that I find actually very exciting, and I will afterwards show you a little simulation that even indicates that. That there can be some highly non-trivial many-body dynamics that comes out from this cascaded master equation in a way that you might maybe not expect it, okay? And one example is here the following. Suppose that I take a system where I take, here's a two-level system that I will drive continuously with a laser, and it can emit photons going here to the right. This one is driven, can absorb photons. One that come from the first atom can be absorbed and be emitted, but it will also be driven by a laser and then go to the right. And so you're really trying to pump all of these atoms at the same time, okay? And then you can calculate, even analytically, the steady state of the system, making certain assumptions, about Rabi frequency that I'm not going to state over here. And then you find something very, very magic, namely that you find that this master equation, that normally if you calculate the steady state of the system, which is in most cases always a mixed state, it turns out to be that it is a pure state, okay? So when in a many-body system you get a pure state, it's like saying that in a many-body system and you can cool in a non-equilibrium way to, well, in this case, the state psi over here, and the question is, what is the state over here? Is it actually interesting? And the answer is, actually the state is remarkably interesting because it turns out that this state is a pure state, but it is a product of EPR state, of dimers. Two atoms are sort of correlated like this as an EPR pair, second one, and then third one, and so on. So the steady state is a dimerized state where these here form, some dimer, an EPR state. This thing here forms a dimer, it's an EPR state, and this thing here forms a dimer. So it's quite remarkable that you drive a system to a steady state, which on one hand is pure, and second, it is entangled in the state of factorizing into these EPR states. You might ask, of course, can we engineer something that's maybe a little bit more complicated, not only pairs of atoms sort of being correlated as a singlet or as a triplet state? And the answer is yes. If you give me more tools to do so, we know how to do that. We can construct states that would form clusters of 4 and so on. But it's quite remarkable. And this is definitely not true if you have, for example, a situation where you have bidirectional coupling. If you have bidirectional coupling, it's something very trivial out, and this thing goes into a mixed state. Like when you do the Bloch equation for a two-level system, it goes to a mixed state, and it's not a pure state, except if you turn all of your lasers on, because then you're in the ground state, and it's a pure state, but maybe not so interesting. So that's an entangled pure state. Was a question here?
What do you mean by EPR state? I'm sorry, I don't know.
Okay, by an EPR state, what I mean by this is the following, that so if I have my two-level system, and I got here ground and excited state of the first one, and then I got here ground and excited state of the second one. This is superposition state where, for example, the first atom can be in the ground state and the second in the excited, and then the first atom in the ground, second excited. These are the states that we need for teleportation. And it turns out that the state here that you get as a steady state is one, which is 2 atoms in the ground state plus then some coefficient alpha. And this is the part which is the entangled state over here, okay? So it is a dimer, sort of, you get non-equilibrium steady states in the form of pure states that form quantum dimers. So if you're a condensed matter theorist, this is actually very interesting that steady state dynamics gives you pure entangled states as a result of driving this thing in a dissipative way. And this is sort of one of the miracles that comes out from this chiral master equation. The very special structure gives rise to these very special states. So if you want to do teleportation, this part is the one which is sort of the interesting one. I'm not suggesting that this is the way to produce the best entangled states over the distance for teleportation, but from a condensed matter point of view, that's quite an interesting statement. It's a non-equilibrium systems with pure states.
What happens if you inject one photon from the left? You will shift everything back.
If you inject one photon from the left, or if you drive the system. So this drive that we have over here can actually come from the left also. So this drive, it's a coherent state, which in this case is simply transmitted. And I will give you afterwards, I have a little simulation that demonstrates how the system goes into this particular state. And let me show you the simulation. This is the intuition behind it. And I think it's clearer than if I try to explain it here by hand. But before I do that I show you this little simulation, I want to ask the question, can we actually engineer in some other systems also this unidirectionality? And there's actually a very simple answer to this story. And I think that the superconducting qubit community could sort of build something like this thing almost immediately, which is the following one, that I argued before that we have spin-orbit coupling in nanophotonics. This was optical photons, where you get this unidirectional coupling, going out with this broken left-right symmetry. Let's do something like that. Imagine that we got an atom over here, and this atom does not directly emit to the fiber, but has a dipole-dipole interaction with an atom over here and an atom over here. So this atom, so we can have the following processes. The upper atom can go down, exciting, for example, this atom that can emit the photon or the other one. But if you put a relative phase in your dipole-dipole interaction between left and right, and this could be interpreted like inserting a flux, if you want, the magnetic field, that you insert over here, chirality, then the photon that comes over here that wants to go left and right, and the photon that comes here that wants to go left and right, is interfered with such a phase that the photon essentially is emitted only to the right. So this is like we can have two emitters that have constructive or destructive interference. So if you construct something like that, this atom first, transmitting the excitation to two atoms over here that couple at different points to the fiber and give them the right phase, then there will be destructive interference to the left and you go to the right. So in this sense, it would be immediately possible to construct, for example, sort of more complex meta-atoms, if you want, that have this property without the spin-orbit coupling. This would be another example. There's the question, can we do it in free space? So we have ideas how to do that, but I will not talk about these things here. And let me show you now one example. That's sort of an example of a calculation that we did a few years ago, which on one hand will demonstrate to you how these dimers are building up, because this is sort of generating the intuition, what's happening over here. And on the other hand, it also shows a little bit the kind of calculation that we do. Before, there were a lot of questions about asking, when is the master equation valid or not, and so on. And this is an example where we take an enlarged system and then make the Markovian cut at a much bigger scale than simply the two-level system. Okay? So let me explain to you what's going on over here. So I have here a first atom and I have a second atom, and both of them I'm driving. Okay? And I said before that we want photons to be emitted into the waveguide. So let me now make a slightly different models, and instead of having a waveguide which consists of photons, I'm making something which is, from a theoretical point, a little bit simpler. I'm considering a spin chain, so I'm replacing my photons by magnons. Okay, just spin waves that can go. And I would like to look at, instead of the radiation coupling, I want to look at the situation here where if this atom goes down by dipole-dipole interaction, it can excite, for example, this atom over here in the waveguide, and then you would have a magnon propagating here to the right or left, but at the same time couples with a different phase over here. So this is exactly this idea that I explained on the last slide, that by coupling this atom to 2 in the waveguide, and giving it the right phase, we interfere out one direction, but we get the other one. Okay, so this is an example of a chiral coupling that you might be able to engineer in a solid-state system, or then even in a case of an atomic system over here. So our waveguide, as you can see over here, is a waveguide that should in principle go to infinity. And what we do now in this calculation is this, that, well, we cannot keep in our calculation infinite waveguide. Some of you might say, well, just make the Markov approximation and eliminate these things over here. No, but here we really would like to see our photons or our magnons propagating in the waveguide and see what they do. So what we do here is this, that we take a spin chain that we would like to be infinity. These are these magnons propagating left and right. But what I do is this, then I'm putting a sink here at the end so that photons or magnons that propagate over here are never reflected. So I'm making an open system by hand by putting the Markovian cut all the way out. Okay. So what you then have to do is this, to solve a many-body master equation that has, count the number of two-level systems that you have over here, but you can do this quite easily as a simulation, and now show you that when we put certain phases over here, what you should get as a result. So let me sort of start this, and maybe I should do this now a few times. On the left-hand side, you can see the electric field which is building up between these two qubits. And what you can see over here is this, that the electric field initially sort of builds up, a light is going out over here, a magnet's over here. But can you see that there's destructive interference, that this atom over here emits light or magnons? This thing emits light or magnons, but the destructive interference over here, the electric field on the right-hand side, or the magnon intensity, is equal to 0. So you have this very peculiar situation that this atom emits photons. These photons are absorbed by the second one. The second one also emits, but overall there's a quantum interference that the light that comes out on one side is equal to 0. So it's a dark state that we are generating that has an electric field in between, but these two atoms act like a little cavity, which is essentially perfect. So the dimers come out by these atoms sort of being correlated in a certain way that they do not emit, that the outgoing photons from both of them, when you superimpose them, interfere to 0. That's exactly what you see over here. And there's no input on the theory side, no assumptions or so. It's just really by solving brute force this master equation, you got these things out. On the right-hand side, you can see the magnons that are being emitted, and this is momentum. So you can see this is peaked over here, and what this thing means is that effectively you get magnons only propagating in one way, but not in the other way, okay? You can see there's a peak for positive k, but there's a minimum here for negative k. This is the reason, and this is an example that we have a chiral system, and the chiral system simply means that overall this block that we have over here and also this one only generates right propagating photons or magnons in this case over here and not left propagating ones. And the reason is quantum interference, because we put in these extra phases to get on the level of the single atom quantum interference that emission only goes essentially one way. Okay? Now what happens to the system spins? Maybe the most interesting part is this. If I have this big density matrix from over here and I calculate the reduced density matrix of this subsystem over here, you can see that the trace rho square of this thing, the purity, it goes to 1. Why does it go to 1? Well, this is a pure dimer in the way that I tried to explain over here. So you can see that as a consequence of all of this, you get a steady state solution of your continuously driven system while you're always trying to put in energy, by the Rabi frequency, but it goes into this dark state, and at the end, it comes out here as a pure state. And this is sort of an example of the magic which is inherent in these chiral master equations, and I just, we can do theory about these things. We can write down many of these things analytically, but that's maybe not the point here. So how are we doing in terms of time? You want to hear a little bit more about this entanglement of dissipation, or I'd be also very happy that we say that I've stressed you out so much today that we need now, there will be free wine, or no, okay, no, okay. Tomorrow, okay, yeah. So who would like to continue? I don't want to overstress you. Okay, so that's good. Wow, you're really enthusiastic, okay. So let me tell you a little bit about this work that we did a few years ago, and this should be considered as, can we get entanglement from dissipation? And at the end, we actually did with Rainer Blatt together, we did the theory side, we had the idea for this thing, and we could convince Rainer Blatt and Christian Roos to do an ion experiment. This was a Nature paper from a few years ago, and let me try to tell you what the basic ideas were behind it. And let me start out with a slide that I've shown now 3 times. This is entanglement by, okay, this is not 3 times, this is references over here. Okay, I've shown you this several times, okay? And you can see that I've added only one small feature to this thing over here, which is the fact, imagine that these ions are undergoing spontaneous emission over here, like spontaneous emission that we have over here. And this, of course, leads to decoherence, and we would say that this is very bad. We are sort of asking here in this context, and to say that there was similar work also at the ETH, in terms of, for example, squeeze state production for the phonons, but this is a many-body version. Here the open spin dynamics and decoherence is sort of bad. We would understand. I mean, all of you know that this would be the formal description for a quantum information person that would simply say you got a system, coupled environment, there's this big unitary entangling these things, and this is the end of the story because now the qubit goes bad, and then you've built a bad quantum computer. How would you describe these things? If I show you this completely positive map, all of you will be very happy because in the meantime you're experts or semi-experts on these things. let me ask you now a different question, and the question is this. Well, we can take sort of the God-given couplings to the environment over here, or we might actually be clever in trying to engineer a certain coupling to the environment. But when you say that we want to couple, to engineer the coupling to an environment, I mean, what do we want to do? We would actually do it to achieve a certain task. And one of these tasks, for example, could be that you say, I want dissipation to drive my system when I apply this map eventually, and maybe it needs several iterations, to a pure state. And maybe this state should even be interesting in the sense of being an entangled state that you generate that some other people might be willing to pay money for, like EPR states or whatever these things are. And so it can be driven by dissipation systems into a pure state, and maybe this state is an entangled state in the sense of being an interesting entangled state that could be useful as a resource in another context. And now the question becomes the one, can we engineer our couplings over here in such a way that we can actually achieve it? And this then means that if you think about the master equation that we did, can we ask our master equation, to engineer the coupling to the environment, all of our jump operators in such a way in a many-body system that the steady state is pure, but at the same time also interesting in the sense of being non-trivial. Okay, this is the question that comes out over here. So to say it more formally, we have here these maps that we might iterate several times. Can we achieve here pure state? This is the desired pure quantum state. So we are sort of cooling into a pure state non-unitary. And on the level of the master equation, you would write down something like that, and you would simply ask, can we do an engineering of these quantum jump operators that we have over here, so that in the long run you get a pure state, but also this entangled state that you want. When normally people see this in this context over here, their immediate response will be, well, that's sort of wishful thinking. But let me remind you that on the level of, for example, atomic physics with lambda systems, this is single atoms, something like this is sort of happening every day. Because I guess many of you might know that if I take a lambda system, the special thing about the lambda system is that we have so-called dark states that are driven over, that the system over here, for example, in this particular case, it's sort of obvious. It's a very special dark state. If I put a pump over here where the electron is lifted up here by the laser, and it can emit over here, but it can emit over here, but we don't have a drive taking it back, then all of you would say immediately, well, this system, obviously, if I just run it, all of the electrons over here will be pumped over here. You're producing a pure state, which is this state over here. This is this dark state. So in optical pumping is sort of a way of doing exactly this thing on the level of single atoms. But we are now asking the same thing on the level of a multi-level system, okay? So, of course, so the question is then one, we have here optical pumping, we have the optical Bloch equations, and it becomes a question of engineering jump operators. And in a more general context, what you want is this. You would like to design here a master equation. This is sort of this inverse problem. I give you a state, like with parent Hamiltonians. This is parent Liouvilleans, I would call it, where you specify states, and we would like to engineer a master equation and the physical realization in such a way that the steady state of this master equation is this thing over here, and there are certain consistency requirements over here in terms of these Hamiltonians that this has to satisfy. So this is now the engineering goal that you would like to achieve, okay? Of course, mentioning dark states, Condanucci won the Nobel Prize essentially for this, ESCPD, where you have these momentum distributions, being sub-recoiled that also go to dark states. So being in France here at the moment, of course, I had to pay your proper reference. And the question that we are asking is now, can we do the same game maybe on a many-body system and engineer master equations that we got non-trivial entangled states out? Okay. I want to illustrate this thing now in the context of a very simple example where all of you will see immediately what the point is of the story and how we can actually construct interesting master equations that do this job. The conclusion at the end will, well, they look horrible, so how do we find a physical implementation? But the answer is that on our quantum machines, we can actually program some of these things. And let me give you this example as the Bell states, or at the end it will be stabilizer pumping. So Bell state preparation dissipative is sort of one example, give you the concept. And as I said, there was at the end an ion trap experiment that it's stabilizer pumping for 4 ion making a GHZ state. Actually quite a remarkable experiment, which was done, I think, 6 or 7 years ago. Okay, so let me give you the task that we would like to solve, okay? We would like to construct now a master equation, or maybe just a Krauss operator if you want, which does the following job. You have a system and you switch on your dissipation. And we want at the end that the system goes, by switching on this dissipation, into a state which is pure, and we want it to be entangled. Okay, so if I take 2 qubits and I ask you what are the entangled states, then all of you would immediately know the answer. This is 2 spins, and we would write down, and in the 2 spins, there's 4 of these Bell states. They are usually classified in terms of this psi plus and psi minus if you read the literature. And so you pick one of these states and you say, can we engineer Krauss operators that if you apply them, put the system, maybe even in a single step, into one of these states, by dissipation. It's Krauss operator engineering, or at the end, write down a master equation which does this thing. And actually, the way to think about this problem, how we can constructively write down jump operators which sort of do this job, is when you think about these Bell states that we are writing over here as stabilizer eigenstates in the following sense. Take x1 and x2, and this is really sigma Pauli matrix, x over here for the first particle, the second one here, the corresponding c, sigma c for the second one. These are 2 commuting operators over here. And it turns out that these Bell states that I'm writing on the right-hand side over here, they are eigenstates of these 2 commuting operators, which are stabilizer operators, we call them. So I can make this little table over here that you can see. I have the 4 states, phi plus, phi minus, psi plus, and psi minus over here. Okay, and these are the eigenvalues. So this state over here has eigenvalue +1 and eigenvalue +1 with respect to this one and this one over here. So this little matrix is just characterized by the eigenvalues that we have for these Bell states as being stabilizer operators. Okay, now our goal is this, that based on this insight that we have over here, can we do some Bell state pumping? So we have talked about optical pumping, which is a way of purifying a state. You have some ground state manifold and an atom, and you optically pump and get a pure state out. That's maybe the stretch state at the very end. So the question is now, how would the master equation have to look to implement this Bell state pumping, that I put any state at the very beginning, and it would always go to the state, say, I don't know, psi minus, to pick one of the states over here. You can pick any state that you would like over here. How would this work? Well, the intuition actually is the following one. What do we do when we do optical pumping? So when we have optical pumping and you have 2 levels over here, and here's your excited state. If you would like to pump everything over here, you put the laser over here that lifts the electron. Sometimes it falls back over here, but once in a while it falls over here. But if it's over here, it's not re-excited back. So all of the electrons are accumulated over here. This is a way of purifying your atomic state. This is optical pumping. It's invented by Kastler, some time ago, I guess. Now we would like to copy the same idea, but now in a many-body system. So how do we implement now optical pumping on this sort of more abstract way? And the way of doing it is this, that I would like to construct here a process that if initially you have some state, which is a superposition of all of them, a mixed state, or I think of a pure state, maybe at the moment I have a superposition of all of these states. I would like to do optical pumping very similar to an atom, where we pump everything, which is a superposition of 2 ground states, into the one over here by applying a pump. And then you would, for example, you would like to find an operator that to do sort of C1, C2, stabilizer pumping from this state to this one over here, changing the eigenvalue of this. And how would you do that? Oops, this is much better here. You would write down a quantum jump operator, and the quantum jump operator would actually have the following structure. It's sort of intuitive what this thing is. So this quantum jump operator has 2 parts. Let's look at the first part that we have here on the right. This first part on the right, you can see that this column and this column is eigenstates of the C12. So 1 plus C1, C2 sort of picks out, simply means this jump operator, when I apply it to a wave function over here, only talks as a projection operator to this first row of atoms. It's like the laser in my optical pumping. I apply a laser that only goes like this, but there's no laser over here. So this is a jump operator that simply say, I only want to talk to the states that are over here. And then what would I like to do? Well, I would like to flip one of the spins that actually puts it over here. This is this operator. Okay, so this is simply engineering a quantum jump operator which does the job. If you apply to any state, if you apply this thing in a master equation, it would simply mean that it cleans up this thing and puts everything over here. Okay? Quite obvious. Now, how do we get these things then down into psi1? Well, you just do the same story that you have over here now by doing stabilizer bumping in this direction. I write down the projection operator that says, I want this quantum jump operator only docked to the upper row. And then, I would like to flip the corresponding spins. And this thing over here, and if you combine these things, you're in the corner, okay? So if you write down this master equation, we'll do the job, okay? But all of you, of course, will tell me immediately, well, it's a very nice answer, but who the hell will give you, a master equation like this? You have to do some engineering, and then your skills have to come in, and this is not entirely trivial. But if you got an ion trap quantum computer, you can sort of engineer the master equation part by some dissipation, and you can sort of artificially construct master equations that are effectively something like this. And this is what we have done. So we have here, two particle operators at the very end. So this is correlated, quantum noise that we have here. Very difficult, but we can actually program it. And in an ion trap, you can easily do that. I will show you results now for 3 ions. And 2 of the ions are the one our system, and then we introduce an ancilla over here. And there's one artificial noise that we can easily introduce, which is simply optical bumping of the qubit. This is what we have available in these experiments. But in addition, I have, of course, all of the entangling operations in an ion trap effectively as a possibility that allow me, and there's certain gate sets over here, including optical bumping, which implement exactly these things that we want. So I'm only saying that if you play around with this thing, we can write down jump operators, and these are sort of Krauss operators here that exactly accomplish the job as a combination of gates and dissipative elements. We just have to play with these things, and there's some details, and I'm not going to do that. So here's the ion trap. This was now this environment ion over here. This is an old slide from these times. And here's now an example where you do Bell state bumping, for example, for 2-step. You start over here. This is down to 1/4 here. And then you apply here a pumping in this step. And this would be the theory curve in 2 steps over here. 1 step, 2nd step, exactly as I explained. And then you can try to do the experiment, and it's over here, and here you can apply it again and again and again, but you're already in the state, and you can see that here decoherence sets in. So this is an example of engineered quantum dissipation, where we engineer Krauss operators. This is really engineering a Krauss operator, not so much the jump operator that I explained before, which do the job of producing interesting steady states that are pure and at the same time entangled, and the Bell state is one example. And you can also do the case where you do this protocol only with a small probability, like what happens in a master equation. In a master equation, this is like a stroboscopic master equation. This is theory, and this would be the experiment, but this is many Krauss operators. This would be the master equation limit, and you can again see decoherence setting in. This would be then the corresponding results of producing, in this case, it was 5+ over here, and then the corresponding tomography. And of course, these things were then done also for much more complicated states, like 1 + 4 ions, to produce then GHZ states. And there's a whole sequence at the end, and you can see the GHZ correlations coming out. So you construct here, essentially stabilizer eigenstates of this one, commuting with this one, commuting with this one, commuting with this one, and you can pump into the subspace, which corresponds to these 4 stabilizers. So it's a 4 stabilizer pumping which is going on, producing then in steady state then this pure, highly entangled state, which is GHZ. You might ask, is it useful? Well, if you do the gates directly to construct these states, you get a much higher fidelity, clearly. Yeah? So it's more demonstrating the effect rather than at that point sort of being the tool that works better than what we have in the lab. So coherent gates, of course, are much more perfect in doing all of these things, but it demonstrates the basic principle. And with this, I'm sort of at the end over here. So this is the end of the 2nd lecture, where by leaving out the theory part over here, I said a few words about this entanglement by dissipation here. I guess that's the end of the story. Thank you.